Hello, this is the Chemistry Cowboy again, and this is just a supplemental video going through example problem of what might be asked on upcoming exam on how to calculate the titrations for a strong acid, strong base. So let's get right to it, looking at this Word document that I put together. So this is a hypothetical practice problem. It is a four-part problem, all interrelated. So reading this real quickly. 37 mils of a solution of perchloric acid is titrated with 0.125 molar NaOH. After titrating 12 mils of base, a pH of 7 is achieved. And then I have these four questions. What is the concentration of acid? What is the pH of solution prior to the base addition? What is the pH of solution after 6 mils of base addition? And what is the pH of solution after 14 mils of base addition? So just leaving those separate, let's look at answers. So we're going to work through these in real time. The numbers I just pulled out of thin air just to work through this. So first thing we should note is that after 12 mils of base, pH of 7 is achieved. That tells us the equivalence point is after 12 mils of base. So the moles of acid equals the moles of base at equivalence. So moles acid equals moles base at equivalence. So with that in mind, we can use the equation MA VA equals MB VB. The molarity times volume of acid equals the molarity times volume of base because of that original setup. So shifting that equation around to solve for molarity of acid, we're going to say MA equals MB B over VA. Or essentially that we have our molarity of base, 0.02125 molar, times our volume of base, 12 mils, divided by our volume of acid, 37 mils. Plugging those numbers in. Now, it's okay that we left those in milliliters because they're both in milliliters, meaning the molarity of our acid has to be 0.00405. We're going to leave it there. Okay, so that's something we're going to use going forward. This is our concentration of acid. Now, because this is a strong acid, there is no Ka expression. We can say that whatever the concentration of HA is will also be equal to the concentration of H plus or H3O plus or hydronium. That we do not have to write an ice table. It's assumed whatever the HA we have is equal to the H plus that remains. So when we calculate our pH is equal to the negative log of our H plus, which equals the negative log of 0.00405, which equals 2.393. There's our pH. Okay. So there's our pH initially before I've added any base. Now, if this was a weak acid, 6 mils would be the half equivalence point. And because of that, we would have to, you would have to be able to, well, I mean, this would be a special significant point in our titration, where half of the acid is neutralized and half the base, by half the base. But because this is a strong acid, this has no real significance. So we have to deal with our titrations and our neutralizations. So we have to break this down into several steps. Step 1 is calculate for our dilutions. Calculate for our dilution. So step 1, dilute. Step 2, neutralize. So calculate moles. Step 3, dilute. Step 4, pH. Okay, so now, so the moles of acid, our moles of acid is going to be MABA. B. Moles acid. And that's going to equal what? Our, is it 0.00405 times 37. Now we can leave these like that as long as we leave everything in mils. If you want to turn this into liters, you have to turn everything into liters, and that's going to make everything a pain. Now I'm going to just leave all the digits just to avoid rounding unnecessarily. So that's for our acid. For our base, MBV equals moles B, and we have 0.125 times 6. Conveniently, this is going to be half whatever the previous number was. Or at least it should be. Let's see. Did I screw something up? I may have screwed something up. Okay. Oh, geez. Okay. Okay. So back here, I made a mistake. Back in problem 1, do this calculation, you get 0.40405, which will change everything on the scale. 0.05. So that becomes 1.393. And this will become 1 0.4985. Sorry for the confusion, folks. Mistakes get made. Now, the magic. How did I figure out I made this humongous blunder? How did I figure that out? Well, because this happens to be the half equivalence point, and I did this math, which should be really easy math, and I got 0.75, which happened to be larger than my moles of acid. Happened to be larger than my moles of acid. I'm like, oh, that doesn't look right at all. And I was able to quickly figure out what's going on. This was off by something. So, little minor error, but you look through that and you go, oh, that's why you always want to check your work. Always check your work. Double check your math. That's fine. So this should be half of that because, well, it's at half equivalence point. So with that in mind, ice table, this is just calculating your neutralization, not a true ice table. So minus 0.75, minus 0.75. Actually, we probably don't need that whole column. Delete that whole column. Let's see. Okay, so with that in mind, how much base do we have? 0. How much acid do we have? Well, because of my rounding, 1.4985 minus 0.75, it's 0.7485. If I had rounded up, it goes to 1.5. It's fine. Now, we're going to redilute. So whatever's left, we have to redilute. So we say, for this guy, moles divided by volume equals molarity. So, but you got to keep in mind, this is now, the volume has changed. Volume has changed. Total. So now our remaining moles, 0.7485, now has to be divided by our total volume, which is 37 plus 6. Recalculating for this. So we say 0.7485 divided by 37 plus 6. And this is why you're okay leaving that as millimoles, because if you divide by milliliters, you get back to molarity. So our concentration of acid has now gone down from 0.045405 to 0.0174. Finally, our pH going to be negative log pH equals negative log of H plus. Now, because remember, we have our, this is strong acid. The strong acid, the amount of H plus left is equal to, amount of H plus left is equal to the amount of HA left is equal to H plus. So we can simply say is equal to the negative log of 0.0174. Or 1.759. So basically, initially, I start at pH 1.393. After half of my acid is neutralized, I jump up by about a little bit over 3.3 pH units, but not very much. Not very much. To 1.759. Reasonable jump. Now the last part of this. What is it after 14 mils of base addition? So please note, we're going to same general things. Calculate moles. We're going to neutralize. We're going to dilute. We're going to, here's where it changed. Calculate pOH, and then finally turn to pH. So let's do this. So same exact steps for this guy. The moles of acid equals what? 0.0405 times 37. That hasn't changed. Would give us 0.14985 millimoles. Now, the only thing that has changed is the moles of base. Moles of base equals still 0.125, but now we are using 14 mils. So I have 1.75 millimoles of base. So now the moles of base, did it again. I did it again. But now the moles of base are greater than the moles of acid. So we're going to still neutralize. Copy. Still going to neutralize, but now we have more base than we have acid. So we're going to neutralize our acid with our base and our base with our acid until one of these guys runs out. So in this case, the amount of acid in here runs out first. So minus 1.4985. So 1.75 minus 1.4985 gives us how much base is left? 0.2515. Now we have to redilute. So still the same equation, still the same. Say, well, no, wrong thing. We go here, we say moles divided by volume total equals molarity. So we're going to say our moles of base, 2515, divided by our volume, so 37 plus 14 now. And that will give us our molarity of base, 37 plus 14. It's not a whole lot. 0.493 molar NaOH. Now, for pOH, you got to remember, for a base, the concentration of NaOH is going to be equal to the concentration of OH minus in solution for a strong base. And POH is equal to the negative log of OH minus. So we're going to take the negative log of our POH, of our OH minus, which we just calculated 0.00493. So that equals negative log of 0.00493, 2.307. Now, the last step, we need to answer the original question of what is the pH? That pKw equals pH plus pOH. So with that in mind, we can rearrange that equation to say pKw minus pOH equals pH. Well, pKw is just 14. So 14 minus our pOH, 2.307, will give us our pH of 11.693. 693. So just by adding 2 mils over the equivalence point, it jumps to a highly basic solution of 11.693. Now, as I keep adding base, it'll get more and more basic and more basic until finally it's incredibly basic. But for now, that is what we have. So this is a hypothetical problem that you could see on a test. So let this be a good lead on how you would treat these problems. Let this be a good way, work this through in practice.